here you see a person walking with a computer-controlled prosthesis. The knee is a computer-controlled, and the foot ankle is a passive foot ankle device. This particular prosthesis is not able to emulate how your knee and ankle and foot works. And because of this, amputees have a higher walking metabolism. They require more energy when they walk. And they walk more slowly. Their natural walking speed is slower than is normal. And amputees have an impaired stability. So this is how your ankle works. Here's mechanical power plotted vertically, and percent gait cycle plotted horizontally. There's 4 curves corresponding to 4 different walking speeds. It turns out when you walk and you go faster and faster and faster, your ankles give you out more and more energy. More energy than a spring can provide. Thanks. And conventional prostheses obviously can't provide those human-like energies. And at the knee, you also see positive power regions and negative power regions. Many of the artificial knees today are only capable of applying negative power, only taking energy out of the amputee as they walk, kind of like a car brake. But the human knee, as you can see from this data, also thrusts, gives power, gives positive power. So because of these differences between the artificial leg and the biological leg, we believe causes the increase in energy, slow walking speed, and stability problems. So what we want to do is understand how the human body works, and then use that knowledge to motivate the design of the next generation of prostheses. So this is not a cartoon, it's actually obeying these laws of motion. You can see the ground is continually changing. This model of the human knows nothing about the ground surface, but it nonetheless can navigate these variations in ground surface without falling over. So what we've done in this model, we've put in the muscles and the tendons and the skeleton, what we believe to be the reflexes to the spinal cord. What's emerged is this extraordinary stability. Such a neuromechanical model informs us on how to design these robotic prostheses. In the last few years, we've been developing the world's first robotic foot ankle system. So here, this gentleman put this robot on 30 minutes prior to this video being collected. You can see his face. He's very happy, very confident. So even though this prosthesis weighs a lot more than a conventional dumb spring prosthesis that's now being used, it's actually behaving in a more human-like way, and therefore enabling this gentleman to walk with normal energies. So we measured the amount of energy used by this gentleman and other amputees using the robot. So here's metabolic cost. And here's three amputees that use the robotic system. And the blue is a conventional prosthesis, and the red is the powered prosthesis. So in this pilot study, we showed that we can lower metabolic cost using this new robotic system as compared to the conventional prosthesis. These numbers, the percent differences here, are very significant. A unilateral amputee, below-knee amputee, is about 10 to 20% higher energy than an amputee, than a normal person. So these numbers suggest that we are very, very close to normalizing metabolism. One of the subjects, we were actually able to increase his walking speed, his self-selected walking speed. And even at that higher speed, we were able to lower his energy by 10%. So with this robotic system, we can We can have amputees walk faster and even at lower energy. So this is how, this is ankle torque versus ankle angle from a normal, healthy biological ankle. So that what the robotic ankle is doing is mimicking this trajectory. And we do that with this robotic architecture. So here's, the ankle has a motor and a transmission with a series spring. The series spring is like the Achilles tendon, represents the tendon. And in parallel, that actuator system, it's in parallel to a spring structure that represents the ligaments that span the human ankle. And with that architecture, we're able to generate very high torques and very, very high powers. In terms of control, how we control this robot, we mathematically model the part of the limb that's missing, the muscles and tendons and reflexes. And then that internal model tells the robot what power to generate, what resistance to provide. So the robot actually behaves as if it has tendons, muscles, and reflexes. So you saw in the previous video that the amputee was wearing a backpack. That backpack had the electronics and the battery. In this newer version, all the electronics are in this box. And the battery is very small, it's just under the pant leg. So we're systematically making it smaller and smaller and smaller and more efficient. So what this previous design doesn't have is an artificial gastrocnemius, or a calf muscle that goes from the knee past the ankle. So we've advanced the system further to include an artificial gastro. So here I'm walking with two robotic ankles and also two artificial gastrocnemius spanning my knee. With this, we're able to get further reductions in energy. In terms of a knee system, again, using models of the human leg, we're designing new artificial knee joints that exploit tendon-like elasticity. With this type of actuator system, which has two motors and two series springs, so it's an agonist-antagonist muscle-like arrangement. We're able to capture the dynamics of the human knee in level ground walking at very, very low